In today's Calculus 3 video, we are going to be covering the chain rule with partial derivatives. And in order to do that, all you have to do is learn how to make this tree diagram, which I will teach. Now, the reason it'd be useful is, for example, if we're looking for del of z over del of t, which this little partial derivative symbol is called del, we would have to look at the top variable and the bottom variable and climb down. So for example, we'll start with the z and find a way to get to this t. Now, how you would do that is you would multiply this entire side together and add it to the multiplication of this entire side over here. And how I did it was I just matched the variable on the top over here, and then I matched the variable in the middle, and then I matched the variable in the bottom. So that's how that tree was made. So you would multiply del of z over del of x with del of x over del of t, and you would add it to the del of z over the del of y times the del of y over the del of t. So let's get into an example. Now in our first problem, we are given our x, our y, and our z, and we're asked to find the del of z over the del of t. Now if you're wondering how to start the tree diagram that I had shown earlier, what I like to do is look at the top variable of the question, which is z, since we are taking the partial derivative of z. So that's going to be the very top. Now z branches off into x and y, because those are the two other variables given. And notice from x, we are given the variable t, so it branches into t. And with y, we are also given the variable t, so it branches into t. And again, I'm finding this through the pieces we're given over here. Now, in order to form what we're going to multiply and add, since we are asked the dz over dt, we're going to have to find a way to climb from here to here. So we're going to go in order of z to x and x to t. So from z to x, we're taking the del of z over the del of x. And from x to t, we're taking the del of x over the del of t. And like I said earlier, all I'm doing is matching the variable with the top to this top, matching this variable of x to this x, and same with this one, and then matching the bottom variable to this t. And if you notice, it's forming some sort of chain. It's an awful chain. And then the same over here, where we find the del of z over the del of y, and then the del of y over the del of t. Now, since we're asked del of z over del of t, we have to multiply this side and add it to the multiplication of this side. So our equation will be del of z over del of t equals the del of z over the del of x times the del of x over the del of t. And we're going to add that with the del of z over the del of y times the del of y over the del of t. And so now with this information, we can just plug in. And so given what we know, let's find the del of z over the del of x. If we take the partial derivative of z with respect to x, we'll treat y as the constant, as if it's like a number, like for example 6. And so I put the z down here, and all we do is take the derivative of x and leave y alone. So it becomes 2xy plus 4y cubed. Now our next step is to find the partial derivative of x with respect to t. And all we do is get our x over here and take the partial derivative, which since 3 is a constant with no t attached, that becomes a 0. And then since there is a t squared, that becomes a 2t. So that is our del x over del t. Now we add it to our del z over del y, which again, our z is given over here. And so now we treat x as a constant, so that gets left alone. So taking that partial derivative, it becomes x squared plus 4x times 3y squared. And then lastly, we take the partial derivative of y with respect to t, which in this case, our y equals 2t to the fourth. So we just take the derivative and we get 8t cubed. And again, this is a result of del z over del t. So let's set that equal. And then we can further simplify this area over here, which is just 12xy squared. And so our final answer, finding the del z over del t, becomes 2xy plus 4y cubed times 2t plus x squared plus 12xy squared times 8t cubed. And that is our final answer. Now our second question is a bit longer as we are given more variables, but don't worry. Our starting variable will be w since, again, our question is asking the partial derivative of w with respect to r. So w will be our top. Now since r is on the bottom, we know that that's going to be on the bottom of the chain, so we'll worry about it later. We see that w is split into x, y, and z, so let's write that down. Now in our x group, we are given the variables r, s, and t, so we can write that down over here. Our y group over here is also given r, s, and t, so we can write that over here. And then lastly, our z group is given r, s, and t, so we're going to write r, s, and t. Now since we're going from w to r, we're going to focus on the ones going in the green direction. So notice all I'm circling is the ones in between, which is the x, y, and z, because they lead us to the r. So we can ignore this s and t on each one. So this is telling us that our x side will be the del of w over the del of x, and then the del of x over the del of r. And then our y value will be the del of w over the del of y, which then proceeds down to the del of y over the del of r. And then our z value will become the del of w over the del of z, proceeding to the del of z over the del of r. And again, if you're confused with the pattern, I'm literally just matching this w to this x with this x as well, and then to this r, with the same pattern occurring with these w's and y's, and this w and z. So I hope a pattern is being recognized here. So now we're going to multiply these two together and add it to the multiplication of these two together, and add that with the multiplication of these two together. So our del of w over our del of r equals the del of w over the del of x times the del of x over the del of r plus the del of w over the del of y times the del of y over the del of r plus the del of w over the del of z times the del of z over the del of r. So to get a better visual, I'll just take our variables up here and duplicate it to move it down here. So I hope you get the gist of it now. To find the partial derivative of, for example, w with respect to x, we look over here at what our w is, and we just derive x, treating whatever other variables are left as a constant. So this becomes 3x squared times y plus 0, because over here there's no x value, so there's no point of adding it. And then our del of x over del of r, we look at our x value over here and derive this one, treating s squared and t as constants. So this becomes s squared times t, and then we add it to the partial derivative of w with respect to y, which gives us x cubed plus 2yz. Taking the partial derivative with respect to r of y gives us 3r squared st squared. And then lastly, the partial derivative of w with respect to z is just y squared, since this one does not have a z over here. And then again, the del of z over del of r becomes st cubed. And that is how you do the chain rule with partial derivatives in one variable, given one variable, and three variables. If you need more help with Calculus 3, or you need help with Calculus 2, I have playlists down in the description below. Thank you very much and goodbye. In today's video, we are going to go over the gradient vector as well as the directional derivative. Now remember, a vector is a direction, and in order to find this direction, we're going to use del, which is the upside down triangle, of f of x of y, which equals the partial derivative of x, and then the partial derivative of y, which is going to be our I and j values, or, our x and y in Cartesian. Now our next thing we need to know is how to do a unit vector, which, if you recall, is just getting a vector. For example, if we get 4i plus 5j, same as 4, 5, and we put it over its magnitude or length, which in this case would be 4 squared plus 5 squared under a square root, or the square root of 16 plus 25, which equals the square root of 41. And then you would just put 4 over square root of 41, comma 5 over square root of 41, which would be your unit vector. Now the reason we need the unit vector is because we're required to use the gradient vector and the unit vector to find the directional derivative, which is just the dot product of the two. So that is the introduction for gradient vector and directional derivative. Now, one thing I wanted to mention here is sometimes you will be given the unit vector, so you don't have to normalize the vector. But if you are given a vector, like let's say the 4 and the 5 I used earlier, make sure you normalize it. And what I mean by normalize it is just turn it into a unit vector and then do the dot product with the gradient vector. Because sometimes they'll just give you the vector or the unit vector. It depends. Now, our first problem is to find the directional derivative of f of x of y, which equals x squared y cubed at point 1, 2 in the direction of the vector v equals 3i plus 4j. Now to simplify all of these words into 4 easy steps, you have to remember that the first step is to find the gradient vector. The second step is to evaluate at the point, which in this problem is point 1, 2. The third is to find the unit vector. And the fourth is to do the dot product of the gradient and the unit vector. So we'll turn this into a checklist real quick, and I'll put it to the side. Now remember, to find the gradient is the equivalent of taking the partial derivative of x and the partial derivative of y and putting it into I and j form. And given our f of x of y being x squared y cubed, our x partial derivative becomes 2x y cubed, and our y partial derivative ends up becoming 3x squared y squared. So we can plug those values into our I and our j. So since we did find the gradient, we could check it off our list. Now our second step is to evaluate at the point. So in this case, our point says it's 1, 2. So all we do is rewrite our gradient into f of 1, 2, and plug in our x as 1 and our y as 2. And again, all I'm doing is plugging our x's and y's in correlation with the 1 and the 2. Now we can simplify this much further into 2 times 2 cubed, which is 8, comma 3 times 1 squared, which is 3, and then 2 squared, which is 4. And finally, our gradient vector at 1, 2 becomes 16, 12. And again, you can always put it into a different form, such as 16i plus 12j. Same exact thing. So we did our second step, which was to evaluate at a point, which in this case, our point was 1, 2. Now our third step is to find the unit vector. And since we're given the direction of the vector v equals 3i plus 4j, which I'll write down here, we have to turn this into a unit vector, which was what I was saying earlier with normalizing the vector given. Now again, sometimes you can be given the unit vector itself on the test, but just remember, if you are given a vector, normalize it or turn it into a unit vector. Same thing. So remember, our formula is the vector over its length, and plugging into this formula, this becomes 3i plus 4j over 3 squared plus 4 squared under a square root, which eventually becomes 3i over 5, since this eventually becomes the square root of 25, comma 4j under 5 as well. And that is our unit vector. So we can check that part off our list over here. Now our last step is to find the dot product of our gradient vector and our unit vector. So our directional derivative equals the gradient times the unit vector. And in this case, over here, our gradient was 16, 12, dot product with our unit vector, which is 3 over 5i, or just 3 over 5, comma 4 over 5j, or just 4 over 5, because I'm going to put it into the vector brackets. And if you don't recall how to do dot product, it's just the i's multiplied plus the j's multiplied, which in this case is 16 times 3 over 5 plus 12 times 4 over 5. Now these two come out to be 9.6 and 9.6, which results our final answer to be 19.2. And that is our directional derivative. And we can finally check that off our list. So in summary, we found the gradient vector by finding the partial derivatives of x and y and putting it into I and j. We evaluated it at the point, which was in this case 1, 2. We found our unit vector, which was 3/5 I, 4/5 j. And then we found the dot product of our gradient evaluated at the point and the unit vector. Now that we know it's not that bad, let's just find the directional derivative of h of p of q, which equals p e to the q at the point 2, 0 in the direction of the vector v equals I plus j. So this time our gradient vector is in terms of h, p, q, which literally changes nothing. This is the same procedure, which if we find the partial derivative of p, we get e to the q. And then taking the partial derivative of q, we get p e to the q. Since taking the derivative in this case changes nothing because it's exponential. So easy peasy, we found the gradient vector. Next, we evaluate this gradient vector at the point given, which is 2, 0. So plugging 2 into p, we get 2 e to the q, which in this case is 0. And then same here, it's just e to the 0. And simplifying further, we know e to the 0 is just 1, so this becomes 1, and then 2 times 1, which we just say 2. So we could check that off our list. Now the next step is to find the unit vector of I plus j, which is the exact same as just saying 1, 1 in component form over 1 plus 1 each squared under a square root, which then becomes 1 over the square root of 2, 1 over the square root of 2, which is our unit vector. And so then we can check step 3 off our list. And our last step is to find the directional derivative, which is the same as del h 2, 0 under the dot product 1 over square root of 2, 1 over square root of 2. And sorry, I forgot to put a square root under here, which we know our del of h of 2, is the same as 1, 2 as found over here. Dot product with 1 over square root of 2, 1 over square root of 2, which then gives us the directional derivative of 1 times 1 over square root of 2 plus 2 times 1 over square root of 2, further simplifying into 3 over the square root of 2, which we can simplify even further since we don't want our radical in the denominator. And a quick refresh on how to do that is just multiply the denominator over its own self. And the reason we do this is because it cancels out the square roots on the denominator. So then it becomes 3 times the square root of 2 over just 2. And that is our final answer. Good luck on your test. Today's Calculus 3 video is going to go over multivariable implicit differentiation, and it's one of the more simpler topics with very little to learn. So if we're asked to find the del of z over the del of x, all we do is just take the partial derivative of x over the partial derivative of z. You just divide the two and you multiply it by -1. Same goes with respect to y, where if we find the del of z over the del of y, all we do is take the partial derivative of y and divide it by the partial derivative of z. And then we multiply by -1, hence the negative. Now if you're having trouble remembering the formulas to use, all you do is just think of it as cross multiplying. And what I mean is notice over here, the del of z ends up having the z on the denominator. So it once was on the numerator over here and it becomes the denominator over here. The same goes with the del of x, where it becomes the numerator from the denominator. And same goes with the del of z over the del of y, where the del of z from the numerator transfers over to the denominator over here. And over here with the del of y, it's at the denominator, so it becomes a numerator variable. And don't forget to multiply by -1 on both of them. So let's get into an example. So our first problem asks, find the del of z over the del of x for x cubed plus y cubed plus z cubed plus 6xyz equals 1. Now the first thing to do is to set this to 0, which we can do by just writing out the equation and subtracting the right side by itself and subtracting the left side by the right side, which is just -1 equals 0. Now the next step is we need to see what we're looking for. Since we're asked del of z over the del of x, remember our top variable z will go on the bottom with an f in front, and our bottom variable, which is x, will go on the numerator, which just gets the partial derivative of x. And note that all of this is negative. Now to find this, we just simply find the partial derivative of x, which in this case is just the derivative of all of the circled ones, since they all contain x. So that's going to be 3x squared plus 6yz. Now for the denominator, we just find the partial derivative of z, which is just the derivative of the 1 squared here, which gives us 3z squared plus 6xy. Now that we have our missing pieces, we could plug into our box, which overall just gives us -3x squared plus 6yz over our f of z, which is just 3z squared plus 6xy. And that is our final answer. Very simple. Okay, maybe this isn't our final answer because we can simplify this even farther to become -x squared plus 2yz over z squared plus 2xy. Now, if you're wondering how I simplified this, I noticed that you could take out a 3 out of each of them, and once you take out that 3, you could just cancel it out, and you are left with these coefficients over here. In today's Calculus 3 video, we're going to find the local extrema and saddle points using the second derivative test. And in short, we just take the first derivative of x and y and set it equal to 0, which will help us find our critical points. Our next step would be to find the second derivative of each of those, and then a mixed derivative, which is shown over here, of the derivative of x, and then finding the derivative of y after finding the derivative of x, and then squaring it, which is used here to find a discriminant, or also known as the Hussein determinant. And then after finding our double derivatives and our discriminant, we can use these rules over here, where given the information of our discriminant and our double derivative, we can find if it's a local minimum, local maximum, saddle point, or an inconclusive test. Now, if you want a visual representation in 3D, a local minimum just looks like a bowl, a local maximum looks like an upside down bowl, and then a saddle point is just a saddle looking shape with its point in the middle. Now, while we're solving these problems, I will go over this checklist, which isn't too complicated. It just goes over the steps on how to solve a problem when it comes to using the second derivative test. So again, we find our first partial derivatives, set it to 0. We'll find our critical points using methods I'll show. We then find the second partial derivatives. We calculate the discriminant with the formula I gave, and then we use the discriminant and the critical points to see whether we have a minimum, maximum, or a saddle point. Now for our first problem, we are asked to find the local minimum, maximum, and saddle points of the equation f of x of y equals x squared minus 2xy plus 2y squared minus 2x plus 2y. Now I'll just summon our checklist over here, and I won't make it too big. But according to our checklist, our first step is to find the first partial derivatives and then equal it to 0. So let's do just that. Our first partial derivative of x equals 2x minus 2y minus 2. And like the instructions said, set it equal to 0. And the reason for this is to find our critical points. Now notice there's a pattern where we could take out a 2 and leaving inside the parentheses gives us an x minus y minus 1 equal to 0. Now dividing both sides by 2, we get x minus y minus 1 equals 0. So we could take that constant to the other side and we get x minus y equals 1. Now for our first partial derivative of y, we do the same exact thing except taking the derivative of every time we see a y. So we get negative 2x plus 4y plus 2. And don't forget to set it equal to 0. Now again, there's a pattern where we can take out a 2 because they're all factorable by 2. So we get negative x inside the parentheses plus 2y plus 1. And we set it equal to 0. Again, we divide each side by 2 and we get negative x plus 2y plus 1 equals 0. And again, I like moving the constant to the right side, so let's do that. Now, if you're wondering how to find our x equals, our y equals, we could use the method of substitution where we could set one of the variables equal to something. For example, this side equals to x equals 1 plus y and plug that in for our x here. Or we could use elimination. So in this case, I'm going to use elimination because if you add these two together, which I will organize in a row like this, we get x plus negative x, which equals 0, negative y plus 2y, which equals positive y, and 1 plus negative 1, which equals 0, leaving us with y equals 0. Now that we know that our y equals 0, we could find x by just plugging 0 into every y we have. So we could plug it either into our first derivative of x or our first derivative of y, but I'll show you both. So in this case, if y equals 0, we get x minus 0 equals 1, giving us x equals 1. Now to check our answer, we could just do the other side as well, where if y equals 0, we get negative x plus 2 times 0 equals negative 1. Further simplified gets us negative x equals negative 1. And it's the same thing as x equals 1. So now we know with this information that y equals 0 and x equals 1. This is important because that gives us our critical point with our x coordinate being 1 and our y coordinate being 0. So that is our first critical point. In our checklist, which I'll make bigger because I could barely see it, we found the first partial derivatives and set it equal to 0. And we found our xy using either substitution or elimination methods. In this case, it was elimination. Now our next step is to find the second partials of f of xx, f of yy, and a mixed partial of f of xy. Now this step is fairly easy, as all you do is get the original first derivative of each, which I'll bring down each of them down here, and just take the derivative once again. So our second derivative of x is just 2, and our second derivative of y is just 4. Now remember, to find the discriminant, we need the second derivative of x, which we found, multiplied by the second derivative of y, which we also found, minus the mixed derivative of xy squared. Now if you're wondering how to do that, notice that the first variable on the fxy is an x, so you just get this derivative, which we already have, 2x minus 2y, and then find the derivative using the y. So over here, you notice there's only one part that has a y, which is negative 2y, so we just take the derivative of that, and our f of xy equals negative 2. So now we have all three pieces needed, which on our third part of their list, we can check out. I like that. And all we do is just plug in. So our discriminant equals f of xx, which is 2, f of yy, which is 4, and our f of xy, which is negative 2, squared. Simplified, this becomes 8 minus negative 2 squared being 4, and our discriminant becomes 4. So now that we know that we have a critical point at 1, 0, and our discriminant is 4, we're going to look at our rules. Now the rules state, if the discriminant is greater than 0, and the second partial derivative of x is also greater than 0, this is a local minimum, and if our discriminant is still bigger than 0, but our second derivative of x is less than 0, that will give us a local maximum. So if you want to remember this easily, just look at the second derivatives and know that the discriminant will always be greater than 0 when looking for a min or a max. Now it's different with a saddle point because it will be fairly obvious when your discriminant is going to be below 0. But if your discriminant does equal 0, that's going to be an inconclusive test and you have to find another way to do it, similar to how we did series in calculus 2. Now notice, our second derivative of x is 2, so our fxx is greater than 0 since 2 is greater than 0. Our discriminant is 4, which is also greater than 0, so our discriminant is greater than 0. This matches exactly what a local minimum would give us according to our rules. Now that we know our point is a local minimum, we can conclude that the point 1, 0 is a local minimum since our discriminant equals 4, which is a positive number, and our second x derivative equals 2, which is a positive number. And that is our final answer. So our next problem is going to ask us to find the local min, max, and saddle points of f of x of y equals y cubed minus 3y plus x squared. Now I'll summon our checklist again, but try to remember this list in general. So we're going to find the first partial derivatives and set them to 0. So f of x equals 2x, which again set to 0, immediately giving us our x, which equals 0, and our y equals 3y squared minus 3, which you can see we could take out a 3, giving us y squared minus 1 in the parentheses equals 0, and dividing both sides by 3, we get y squared minus 1 equals 0, y squared equals 1, and finally y equals plus minus 1. So because of this 0, because of the plus minus 1, we have two critical points. Our x stays the same in both points, being 0, 1, and 0, -1. We can check off finding our first partial derivative and setting it to 0, and then finding our critical points using substitution or elimination, which I don't even think we had to use. Now our next step is to find the partial derivatives the second time. So bringing down our first derivatives, we just take the derivative of our x again using x, giving us 2, and then we set our first derivative and take its derivative again using y, giving us 6y. And don't forget, we need to find our mixed derivative f of x of y, which is just 0, since our first derivative of x doesn't even have a y, so it's just 0. Now plugging into our formula of our discriminant, which equals the second derivative of x times the second derivative of y minus the mixed derivative of xy squared, we get 2 times 6y minus 0 squared, leaving us with 12y as our discriminant. Now since we know our points being 0, 1 and 0, -1, we could see how each of these points fit our discriminant. So at 0, 1, which remember, this means our x is 0, our y is 1, our discriminant equaling 12y becomes 12 because we're plugging in 1 to our y. And at the point 0, -1, our discriminant at 12y equals -12, since we're plugging our y as -1. Now again, remember, this is our discriminant at this certain point, and this as well. And we can check back that our double derivative of x, which is over here, is 2, which is a positive number. So that means our double derivative of x is greater than 0. Our discriminant over here is a positive number, so that shows that our discriminant is greater than 0, meeting the requirements for a local minimum. Now over here, we don't even have to look at our double derivative of x because, look over here, our discriminant is a negative number. And going back to our rules over here, if our discriminant is less than 0, this gives us a saddle point. So this eventually rules out to be our saddle point. So our conclusion could be the point 0, 1 is a local minimum, and the point 0, -1 is a saddle point. And there you go. That is our final answer. Thank you guys for watching, and good luck on your exam. Oops. In today's Calc 3 tutorial, we are going to go over tangent planes and linear approximation. And while this does look intimidating with the equation given over here, it really isn't that bad. I'll just explain how it works. But at a given point, x0, y0, and z0, we're given the equation z minus z0 equals the partial derivative of f with respect to x of x0, y0 times x minus x0 plus the partial derivative of f with respect to y of x0, y0 times y minus y0. Now as a reminder, x0, y0, and z0 is just the point where the plane touches, and then the partial derivative of f with respect to x is just the rate of change in the x direction, and the partial derivative of f with respect to y is just the rate of change in the y direction. Now for the linearization part, which is given here, it looks super complicated, but once you get your tangent plane, this is extremely easy. So let's get into a problem. So our first problem asks us to find a tangent plane to z equals the square root of x squared plus y squared at the point 3, 4, and 5, and use it to approximate f of 3.01, 3.98. So just like the previous tutorials, I'll just summon a checklist, with the first step being given as find the partial derivatives. Now we can rewrite z equals x squared plus y squared in parentheses to the power of 1/2, since it's the same thing as this. But we also know that the derivative of the square root of x equals 1 over 2 square root of x. So with the exact same logic, we can just simplify our partial derivative of f with respect to x as 1 over 2 times the square root of x squared plus y squared times 2x, because we use chain rule to find the derivative of the exponents under the square root. Now the same exact thing goes for when we find the partial derivative of f in respect to y, where it becomes 1 over 2 times the square root of x squared plus y squared. But since we're using the terms of y, this x squared disappears, and we just multiply by 2y. Now simplifying even further for both of these, this can become 2x over 2 times x squared plus y squared, and this can become 2y over 2 times x squared plus y squared. And then we could cancel out the 2's, leaving us with x over x squared plus y squared under the square root, and y over x squared plus y squared under the square root. We can now check the first part off our list and look at the next part, being evaluate at the point given. So in our problem, we are told that our point is 3, 4, and 5, which I'll write down here. And we know that that 3, 4, and 5 is the same as our x naught, y naught, and z naught. So all we do is just plug in these numbers into the equations we wrote over here, giving us 3 over the square root of 3 squared plus 4 squared. And on this side, 4 over the square root of 3 squared plus 4 squared. Now, of course, both denominators are the same, and they simplify to the square root of 25, which then gives us 5. So then this becomes 3/5, and this becomes 4/5. So far, I just got the partial derivative derivatives with the given equation, and I evaluated it at the point given. So I'll give these labels as respect to x and respect to y. So now we can check step 2 off our list. Now our next step is to use a tangent plane formula, which if you recall is this formula over here from the beginning. And because this looks so complicated, it looks overwhelming to memorize, but in reality it's not. All we do is just mark out these x naught and y naught and x naught and y naught. Since that's just too specific, there's no point of remembering that. So we can look at it as z minus z naught equals respect to x times x minus x naught plus respect to y times y minus y naught. And this is a lot easier to remember and look at. So we literally know all of these variables. Again, reminder that our point is 3, 4, 5, which is again x, y, and z. And given our points of respect to x and respect to y, all we do is plug. So this becomes z minus 5 equals 3/5 times x minus 3 plus 4/5 times y minus 4, which we could turn into decimals if we wanted, and that is what I prefer. So I'll rewrite it really quickly. 3/5 is the same as 0.6, 4/5 is the same as 0.8, and now all we do is distribute. So this becomes 0.6x minus 1.8 plus 0.8y minus 3.2. We can then add the 5 from the left side, giving us 0.6x minus 1.8 plus 0.8y minus 3.2 plus 5. Now luckily enough, negative 1.8 minus 3.2 just becomes negative 5, which then means we could cancel this 5 and this 5. So we are now left with z equals 0.6x plus 0.8y, which is our tangent plane. Now that's the first part, but now we need to go to the second part, which is use linear approximation with the points given. So we are asked to approximate with the points 3.01 and 3.98. And so looking at our linearization formula, we recognize that this L is the same as our Z. And so we can replace that Z with L equals 0.6x plus 0.8y. We could then evaluate our L with the 3.01, 3.98 given, which is just substituting numbers into x and y, leaving us with these values. Now, after further evaluation and simplifying, our final answer becomes 4.99. So our final answer is that our tangent plane is z equals 0.6x plus 0.8y, and our approximation is L equals 4.99. And so that is how you do the tangent plane and linear approximation. Thank you guys for watching, and good luck on your exam. Before this tutorial begins, I did keep making a mistake throughout the video in the intro where I kept saying that this was lambda, but that is wrong. The two constraint formula is the del of f equals lambda del of g plus mu del of h. So I apologize for that mistake. This is mu, not lambda. Thank you. In today's video for Calculus 3, we are going to go over Lagrange multipliers, and we have two main formulas that we want to focus on. One being the single constraint formula, where you're given one constraint, and with this formula, you'd be following del of f equals lambda del of g. Now, the two constraint formula is just adding a lambda del of h, which corresponds with the second constraint, since the lambda del of g corresponds with the first constraint. Now, for the single constraint formula, we will be given a system of equations to work with, where it separates f into three partial derivatives, x, y, and z, and we simply set it to lambda g of whatever variable is attached. So again, that would be x, y, and z. Now for our constraint, that would be the fourth part of the system of equations, which in this case would be g of x, y, z equals k. Now with the two constraint formula, this g only corresponds with a g here, so we need one that corresponds with the h here. So all we do is add a fifth part to our system of equations, which is just h of x, y, z equals c, and this would be considered the second constraint. And so we will go over a problem with one constraint and a problem with two constraints. For our first problem, we are asked to find the maximum value of f of x of y equals xy with the constraint x squared plus y squared equals 8. Now remember, our equation for our Lagrange multiplier with one constraint is del of y equals lambda del of g. Now to figure out which one is our del of f and our del of g is going to be our constraint. Now, if you're ever having trouble finding the constraint, like let's say your equation doesn't say with constraint, it just gives you two of these equations, you immediately have to look for a constant. Now, does f of x of y equals xy have a constant? No. Does x squared plus y squared equals 8 have a constant? Yes, the 8 right here. So that will be our constraint. Now it's time to find the gradient of both our equation and our constraint. So for our equation f of x y equals xy, we simply just find the partial derivative with respect to x, which in this case would just be y, and our partial derivative with respect to y, which is simply x. Now the reason we're doing this is, if we recall, our gradient becomes a vector. So in this case, since we know with respect to x equals y and with respect to y equals x, our gradient will be yx. Now for our constraint, which is x squared plus y squared equals 8, we simply find the partial derivative with respect to x of g, giving us 2x, and the partial derivative of g with respect to y, which gives us 2y. So our gradient vector for g is simply 2x, 2y. So now we can start our system of equations, and we can start with our x coordinates, which in this case is y and 2x. And remember, we're plugging into del of f equals lambda del of g. So in our x coordinates, our del of f is y, as shown here, equals lambda del of g, which our x coordinate in del g is simply 2x. So that becomes 2x. And with our y coordinates, we know that our y coordinate in del of f is x, and our y coordinate in del of g is 2y. So we could simply set this to x equals lambda 2y. Now for our next part of our system of equations, we're plugging this all into the x squared plus y squared equals 8, which is our constraint. Now if you're wondering why I'm not putting down the fourth constraint, which is the z coordinates, that's because we don't have z coordinates. So with these system of equations, all we do is just sub in for each other. So for our x coordinates, let's solve for lambda. Lambda equals y over 2x. And since we know our lambda equals y over 2x, we could sub that in for our lambda given in the y coordinates. So this becomes x equals y over 2x, which replaces the lambda, times 2y. This then simplifies further to x equals 2y squared over 2x, which then further simplifies to 2x squared equals 2y squared, which even more simplifies into x squared equals y squared. And since we know x squared equals y squared, we could simply substitute our y squared in our constraint as x squared. So this becomes x squared plus x squared equals 8. Now if you're confused on what I did, again, I just subbed in the x squared for y squared given in the constraint. So simplified, this becomes 2x squared equals 8, x squared equals 4, and x equals plus or minus 2. Now solving for y is very easy because all we do is just plug in a plus or minus 2 into the constraint. So let's say 2 squared, negative 2 would be the same thing, plus y squared equals 8, simplifies to 4 plus y squared equals 8, simplifies to y squared equals 4, giving us y equals plus or minus 2. So now this gives us our coordinates or test points, which we could set as 2, 2, negative 2, negative 2. And again, I'm just mixing up the possibilities with the x and y since there's positive and negative. We can do 2, negative 2, and lastly, negative 2, 2. Now, if we test these points into the equation f of x of y equals x, y, then we set each of these points equal. Our 2, 2 would become 4. Our negative 2 would become 4. Our negative 2, 2 would become negative 4. And our 2, negative 2 would become negative 4. So this concludes that our maximum value is the biggest number, which, of course, out of all of these would be 4. So in conclusion, our maximum value is 4. And if we're asked the minimum value, we just look at the lower number, which is negative 4. So those could be our final answers. Now our second problem states to find the extrema of f of x of y of z, which equals x plus 2y plus 3z on the intersection of the plane x minus y plus z equals 1, and the cylinder x squared plus y squared equals 1. Now while I solve this equation, I want you to solve it first, and then I'll quickly run through how to do it. So remember, our formula for two constraints is del of f equals lambda del of g plus mu del of h. Now finding the gradient of del of f, we simply get 1, 2, and 3 when we do take the partial derivatives of x, y, and z. For our del of g, which is just our first constraint, being x minus y plus z equals 1, we get 1, negative 1, 1 as our gradient vector. And then lastly, for our del of h, we get 2x, 2y, 0 as our gradient vector. And this del of h is based off the cylinder. So now this gives us enough information to set our system of equations. And following this exact form, we get 1 equals lambda plus 2 mu x, which is our x coordinates. For our y coordinates, we get 2 equals negative lambda plus 2 mu y. For our z coordinates, since we are multiplying this 0, this simply leaves us with 3 equals lambda. And then for our fourth and fifth part, it will simply be our constraints from the plane and the cylinder. Now, since our z coordinate tells us that lambda equals 3, we could simply just sub in every single lambda we have for 3, meaning that all we have to solve left for is our mu. So in this case, since lambda equals 3, 1 equals 3 plus 2 mu x, which then solves into x equals negative 1 over mu. And then same thing here, except we have a negative lambda, so it becomes 2 equals negative 3. plus 2 mu y, which equals y equals 5 over 2 mu. Now, if we want to solve for mu, we can simply put it into our cylinder constraint. Since our plane constraint has a z and we don't have that information, so it'll be simpler to use this constraint and plug in what we found for x and y. So this becomes negative 1 over mu squared plus 5 over 2 mu squared, which equals 1. And then we can simplify further into 1 over mu squared plus 25 over 4 mu squared equals 1. And since we can cancel out these bottom numbers by simply multiplying this top part by 4 mu squared, we get these terms canceling out, leaving us with just the 4. And the 4 mu squared also canceling this out, leaving us with 4 plus 25 equals 4 mu squared. Since we also multiplied this side by 4 mu squared. This then simplifies into mu equals plus minus the square root of 29 over 2 once you calculate it. And so now that we know our mu equals plus minus square root of 29 over 2, we can simply plug it in to our equations here to solve for x and y. So when we do that, plugging in mu here and mu here, we get x equals negative 2 over the square root of 29, y equals 5 over the square root of 29, and what's missing? Our z, which remember is found in x minus y plus z equals 1. So x minus y plus z equals 1, and then plugging in for x, negative 2 over square root of 29 minus 5 over the square root of 29 plus z equals 1, which eventually simplifies into z equals 1 plus 7 over square root of 29. And remember, it's plus minus for the mu, so we're going to have to do the same thing, but with a negative number on the mu, which when we do that gives us z equals 1 minus 7 over the square root of 29. So this could be either 1 plus 7 over square root of 29 or 1 minus 7 over square root of 29. Now we have to plug all of these into our original equation, which was x plus 2y plus 3z. And when we do plug it in for both possibilities of the z, we end up getting our f to be equal to 3 plus square root of 29, and our other f being f equals 3 minus square root of 29, which the positive one / the higher number becomes our maximum, and our lower number becomes our minimum. So those are the constraints of this problem. Thank you guys for watching. Good luck on this exam.